Hello and welcome to another OCT forum video. This is the first session on OCT normative data. OCT has transformed clinical practice for optometrists and ophthalmologists massively, and B-scans tell us so much more than we could ever know before OCT came along. It certainly transformed retinal practice. OCT's output a great deal of data. A range of maps and normative plots have been designed by manufacturers to help us more readily interpret this data. However, we've got to understand the limitations of the data as well. So in this first session on OCT normative data, I'll briefly introduce you to some of the primary maps and charts normally found in OCT. I have in this case primarily used images from the NIDEC OCT. So here we have what we call a macular map from the NIDEC device. So let's take a look at what this is actually showing us. So top left here we've got the retinal thickness map, which is giving us the retinal thickness in microns on the scale on the side. Next to that we have the early treatment diabetic retinopathy scheme chart, which is a normative data chart. Next to this we have the G chart, which is measuring ganglion cell complex and comparing it to normative data. And then next to that we've got the thickness map for the ganglion cell complex. Bottom left we've got the full normative database map, and next to that the deviation map, both of which represent total retinal thickness, and on the other side the normative data chart and the relative thickness chart are for ganglion cell complex. Essentially, the left hand side of the macular map concerns total retinal thickness, and the right hand side of the macular map concerns ganglion cell complex and therefore glaucoma. Now let's look at the retinal thickness map in more detail. So retinal thickness maps are incredibly useful and sometimes I think they're overlooked by clinicians. Treat these maps as though they are real maps. I got this little analogy from a colleague some years back. So blue colours are the sea, are the lowest lying or thinnest areas. Green areas are the lowlands and grasslands, they're slightly higher or thicker areas. Yellows and reds are hills and mountains, so they are higher or thicker areas. And where we have white areas, these are the snow-capped peaks, the highest or thickest points on the map. And get used to what's normal on a thickness map. You'll expect the peripheral retina to be blue or only light green, and you'll also expect the fovea to be blue or light green. You'll expect the parafovea of the macula to be slightly raised and therefore deeper green or even yellow, what I might call the macular donut. There will be raised areas for the nerve bundles and vessel arcades, superior and inferior to the disc, and sometimes nasally as well. So you'll expect red and white areas there. So get used to that, and if there's any deviation from the norm, you'll then understand that some form of pathology may exist. And so here's an example. We have a snow-capped peak here in the centre. It's clearly not normal. And so we may ask, what is causing this? Well, take a look at the shape. It's very round and regular, and normally that would imply that fluid is one of the causative factors here. And in this particular case, it was a central serous retinopathy, a CSR, sometimes known as CSCR as well. In this example, again, we have a snow-capped peak centrally, a very raised area, but it's very much more angular and irregular, and in those circumstances more likely to be caused by some form of tractional lifting. And in this particular case it was a very, very substantial epiretinal membrane, ERM. And in this particular example, again, we've got lifting. It's not central, but it was caused again by traction, in this case vitreoretinal traction, or VRT, which of course if it was central would be called vitreomacular traction. In this image, the optic nerve head is very much raised, and we can see that it's beyond the disc margin. It's quite a large area that is lifted. So it could potentially indicate a raised or swollen disc, maybe papilledema or papillitis. It could theoretically be caused by buried disc drusen, though normally you don't see quite such dramatic lifting in those circumstances. And in this particular case, it was in fact papilledema. So let's have a look at the actual normative data plots. The ETDRS 9-sector plot is not a thickness map, it's a normative data plot. And the original study, the diabetic retinopathy study scheme, was set up some years back, and it's a map of the macular area so that any data that was reported back would be normalised. And since then, because it's a well-recognised map of the macular area, it's been used by the majority, if not all, OCT manufacturers as a map of macular thickness. The numbers within each sector are the average retinal thickness, total retinal thickness, in microns within that sector. Not something that you'd be expected to know, of course. So the green just means that in this particular case, that patient's retinal thickness is about average for their age, gender and ethnicity. So although it is now used commonly on most OCT platforms, this map was not designed for OCT. Where the central foveal thickness is over 400 microns in many cases of around clinics globally, that is considered a trigger point for consultants to consider intervention with anti-VEGF or other treatments, for example. So think of the scale on the side as a bell curve. It's not obviously a thickness scale. So when it comes to total retinal thickness, the range of normals is very large. So do bear in mind you'll have lots and lots of people with red and yellow areas on these ETDRS charts who are perfectly normal, perfectly healthy. So it's really important to remember that OCT data is quite narrow, and the second part of this, the second video in this little series will actually look at that in more detail. But don't use the colours as a traffic light system. They are not supposed to represent that. They're rather unfortunate choice of colours, really. Red does not mean you must refer. It just means that in this particular case, if it is red, that retina is thinner than most of the normative data. But the normative data is incredibly narrow and small, so it could be perfectly normal for that person, and really changes over time are more important to actually measure. On the NIDAC OCT, the ganglion cell complex is considered to be the ganglion cell layer, the inner plexiform layer, the inner nuclear layer and the retinal nerve fibre layer. On some devices, the ganglion cell complex is simply considered to be the ganglion cell layer and inner plexiform, whilst on others it does include the nerve fibre layer. Ultimately, glaucoma is apoptosis or programmed cell death of the retinal ganglion cell. And the retinal ganglion cell is a neuron, and like all neurons, it has an axon which passes from the cell body to the brain, which is the retinal nerve fibre layer. The cell body itself is the ganglion cell layer, and then it has dendrites and synapses which go into the inner plexiform and inner nuclear layers. And what happens in glaucoma is the cell gets sick. It doesn't just immediately die, it gradually dies off. And very often, the dendrites are the layers that tend to thin out first before the cell dies, and often, whilst the cell is still sick but functioning, the axon, the retinal nerve fibre layer, isn't really affected as much. And so it's quite possible in many cases to see thinning of the whole ganglion cell complex, including the IPL, earlier than loss of RNFL, particularly around the optic nerve head. So it's very useful to look at the ganglion cell complex as an early indicator of possible glaucoma. So looking at this particular example from the NIDAC device, the greyed out circle is the foveal pit, where of course we don't have those inner retinal layers that make up the ganglion cell complex. And of course, because of the nerve fibre layer temporal raphe, it's useful to compare superior and inferior thickness of these layers, because they may differ quite significantly within the eye in early glaucomatous cases. When we look at the full normative database map, on some devices it's a square 9x9mm database centred on the fovea. On other devices it's a square 6x6mm normative database centred on the fovea. And likewise on a disc, it's usually 6x6mm centred on the disc. So the ETDRS only covers the central 6mm. And so it's important to look at the full normative database to see if there are areas that are much thinner or thicker than expected. The deviation map just tells us in percentage terms how much thinner or thicker a point is in relation to the normative data for that point relative to that particular age, gender and ethnicity. Disc maps measure the retinal nerve fibre layer thickness and compare that to normative data around the optic nerve head. They usually comprise a full 6x6mm square scan centred on the disc, as well as a disc circle scan, which is usually about 3.4mm in circumference. And it compares that particular retinal nerve fibre layer thickness for that patient to normative data. So if we look at the T-SNIT, as we often call it, or N-STIN here, this particular chart, it's almost like a panoramic view that's been unfolded flat. If you could fold the two edges here where it says T for temporal, they would meet and form that circle around the optic nerve head that you can see here. And so where we've got the two peaks, the two lumps for the superior and inferior nerve fibre bundles, that's what we hope to see in a normal eye. And the black line here is the patient's own retinal nerve fibre layer thickness. Again, there's no known condition where there's essentially too much RNFL, so we're only interested in thinning. So whole here represents the average RNFL thickness around that circle. Superior and inferior comparison again can be useful to see if there's anything like a nasal step, for example. You can check if the isn't rule has been met, and you can look for any clock hour losses which might represent notches. And in glaucoma on OCT, very early, you often see changes supratemporal and infratemporal at the optic nerve head. OCTs will always produce a CD ratio which is much bigger than what any of us would consider it to be, and that's because the OCT looks at the opening in Bruch's membrane to delineate the disc margin, and we can't see that. We look at the top, or the innermost part of the disc, and see a much larger disc area, hence why we have much smaller CD ratios. Disc maps on OCTs that don't have eye trackers are less reliable and repeatable than macular maps, and I find macular maps or mesh scans at the macula are perhaps more repeatable and reliable for glaucoma. The problem, as we'll see in the next discussion, is that even then normative data on OCT, particularly obviously therefore for glaucoma, is not particularly useful in reality. Here we have a full disc map in this particular case from the NIDEC device, and you can see we've got the full normative database here on the top left. In the centre we've got the RNFL thickness map. Again, think of the map, the blue is the C, etc., as I mentioned earlier, and we've got the OCT disc scan or phase scan on the right there. You can bring up both macular maps or mesh scans on most devices for both eyes together, and the same applies to disc maps. So here we've got a bilateral view of disc maps, and one thing that it does provide you is a symmetry score. Now, there are no clinical papers out there that tell you what a good symmetry score is, etc., but really, if there's a symmetry score of, say, less than 50-40% roughly, that's very poor symmetry and could indicate a marked difference between the eyes, which might show a risk of pathology, including potentially glaucoma. Now, the key to normative data is measuring change over time. And in reality, in those circumstances, you compare the patient to themselves as opposed to normative data. So here's an example of ganglion cell complex progression. So the first scan here, registered to baseline on the left, has taken place, and clearly there's some asymmetry within the eye there that has probably prompted some suspicion. And all subsequent scans are compared to the baseline scan. And you can see over time, superiorly, there is no change in ganglion cell complex thickness. But inferiorly, there is this gradual loss that you can even see on the difference maps here, and what will become an arcuate scotoma. And you can see how it obeys the horizontal midline, which is very, very important and useful to be aware of. And gradually, inferiorly, you can see this consistent loss. Now, how do we know it's clinically significant? Well, in this particular case, it gives us a p-value where the slope is steep enough to represent a pathological loss. In other words, it does what we call a null hypothesis, and the p-value shows that in this case there is definitive change as opposed to no change. And so it fits a pattern of pathological loss, and where the p-value is less than 0.01, that's a very, very strong fit to that pattern of loss. Now here, when we look at disc map progression For the same patient, starting a little later, it's still all green because it can take a while for retinal nerve fibre layer loss to catch up to ganglion cell loss. Until the actual cell is dead, very often the axon will be present. In other words, the RNFL won't be lost. But again, there is this definitive downward slope for the inferior RNFL, and there's a p-value of less than 0.05, which I would say is a moderate fit, or a weak fit to weak to moderate fit to a pattern of pathological loss. If it doesn't give a p-value, then there isn't any pathological loss, basically. Now, sometimes the computer gets it wrong, and that's perfectly understandable. It might be poor image quality, etc. And here it says scan position is not found. Something similar will occur on other OCTs, and it may change the reliability score, for example. What you can do, particularly on this, on the NIDIC device, but I believe you can do it on other products as well, is you can compare the baseline to the particular follow-up scan, choose between 3 and 5 points, usually vessel crossings or bifurcations, and you line them up on the following scan and then save it, and the result is it then lines up the scan properly and gives you a more realistic situation. So, apoptosis of the retinal ganglion cell. Glaucoma is essentially a retinal disease. The optic nerve head is comprised of the axons of the retinal ganglion cells, and thus it is part of the retina. And in glaucoma, ultimately, apoptosis or programmed cell death of the retinal ganglion cell takes place. Whatever the trigger, this is the process. And it takes a very long time for the retinal ganglion cell to die. And in the early part of the disease, dendritic thinning takes place, and the shrinkage of the GCC is observable, often well before axonal loss takes place in many glaucoma cases, and thus the GCC at the macula can define glaucoma sooner than OCT of the retinal nerve fibre layer at the optic nerve head in many cases, and also therefore OCT can spot glaucoma very, very much sooner than visual fields, or when we can spot the damage visually in the eye. Now that isn't necessarily a good thing, as we'll see in the next slide deck. But that is what actually happens, is loss of the retinal ganglion cell, damage to ultimately the whole cell, the neuron. But primarily, initially, it's dendritic thinning that tends to take place before the axon dies, unless it's a very specific form of glaucoma where axonal cell death occurs due to problems with axonal transport. And here's an actual OCT-B scan of a normal ganglion cell complex against a patient who's got glaucoma, and you can see a marked difference, particularly here where there is significant loss or thinning of the ganglion cell complex. It's quite late stage, and you wouldn't normally be able to diagnose glaucoma by looking at a B scan. So thank you very, very much indeed for listening.